Welcome to our Cisco Live 2020 video series. My name is Ricardo Garcia Duarte. I am a technical consultant engineer from Mexico City Wireless Tech. Today, I will be presenting you how to troubleshoot COT 9100 series access point speeds. Let's begin.
Troubleshoot COT 9100 series access point speeds. The COT 9100 series introduces the capability to run 802.11ax, more commonly known as Wi-Fi 6. As technology evolves, more and more bandwidth is needed for the multiple services and applications that are run by businesses, sometimes demanding for high reliability, other times for high speeds. Here, I will teach you how to configure and understand how speeds are managed by these access points so you can ensure the desired bandwidth and throughput for your wireless clients. In the agenda, we have 4 sections. The first one being supported hardware. What is it that the access points need for an end-to-end high-efficiency wireless traffic flow? Second, WLC or wireless LAN controller and AP configuration. What checkboxes do I need? Do certain settings intersect or go against my type of deployment's best practices? Third, verification and troubleshooting. Are my wireless clients connecting at 11ax? What commands do I run on the AP if I suspect not, or not as fast as I need them? Fourth, takeaways. What would you learn from this presentation that you can apply to your own environment in order to exploit and take advantage of Wi-Fi 6? Who is this for? This is ideal for wireless network administrators who need to deliver high bandwidth requirements. For example, there is a store. This store has a dozen tablets for customer use in a showroom. The wireless tablets stream video that used to be high definition but now is turning into 4K ultra high definition, causing jitter. The store would definitely benefit from 11ax technologies for the video streaming service. Also, this is for design engineers who need more than a general overview in order to plan ahead for a migration plan or new technologies such as augmented reality. Technical personnel who needed tools to resolve performance issues when users complain about not getting the speeds they expected. Or simply for wireless enthusiasts who want the full Wi-Fi 6 experience. And the first section is here, supported hardware. The 11ax access point family consists currently of 4 AP models. The 9115 with a 4x4 2.4 GHz radio, a 4x4 5 GHz radio, and a Bluetooth Low Energy or BLE radio. The 9117 with the same characteristics as the 9115, except for the fact that the 5 GHz radio works on 8x8 with 8 spatial streams. This is 8 transmitters and 8 receivers. Then we have the 9120, a 4x4 2.4 GHz radio, a 4x4 5 GHz radio, a Cisco RF ASIC, which takes care of processes such as RRM, and a BLE radio. And finally, we have the 9130, an AP with 4 radios, a 4x4 2.4 GHz radio. Then we have an 8x8 plus a 4x4 GHz radio for a total of 12 spatial streams for demanding clients, a Cisco RF ASIC, and the BLE radio. Regardless of the AP model that you choose, there are important considerations to take into account, referring to the wire network. Starting with the access point switch ports, the multi-gigabit or port use or MGig. A network can sometimes resemble a tree, with the access points acting as the tips of the branches, and a tip is never thicker than a branch. In reference to the access point switch ports, the multi-gigabit port of an access point can give us up to 5 gigabits of speed. However, it's important that our uplinks from the switches are 5, 10, or more gigabits to avoid a bottleneck. This is mandatory for a healthy traffic flow. Know your cabling distance. Under 100 meters is usually a safe distance, but if you go over it, it may present performance issues. Talking about the same cable type, Cat5 is no longer supported for 11AX. Cat5e works but may present limitations. Cat6 or 6A is recommended. Now about the access points, are they going to be in local or flex connect mode? Because depending on that answer is the mode in which the switch port should be. Access or trunk? Is the traffic going to be centrally or locally switched? This is also a mandatory point. And the PoE or power over Ethernet. Are we giving the access point the correct wattage? If not, the AP will still operate, but may scale down from 8 to 4 or from 4 to 2 spatial streams. And this will impact the performance of the wireless clients and the bandwidth and throughput that they can use. Now let's take a look at the other side. On the wireless controller, what is the purpose of the network? To provide basic connectivity to a high number of clients? Or is there a specific number of clients with a 1 gigabit link? Whether it's a Flex Connect 2-hop connection or a centrally switched WLAN, you need to consider the bandwidth of the uplink of the switches. If you do need to centrally switch, add the capabilities of the controller. That could be either 10, 40, or 80 gigabits, so that all traffic smoothly flows from the wireless controller to the access points, from wide to narrow, just like the branches of a tree do. And this is how it looks. At the far left, we have all these wireless clients, which are our birds, looking for the Catalyst 9100 series access points, which in turn connect to the access switches that could be 9200, 9300, or 9400 series. These switches can not only provide the 30 watts of power that a Wave 2 AP would need, but also up to 60 or even more watts, enough to power any of the Wi-Fi 6 APs. The access switches in turn connect to a 9500 or 9600 series core switch, which could have 25 gigabits, 40 gigabits, or 100 gigabits of uplink. That's where our controller connects. That's where we could have our 9800 series controller. And this is the end-to-end Wi-Fi 6 solution. Enough talk. Let's see some configurations. Here's what you need. If it is an ARS controller, version 8.10.112.0 or higher. If it is a 9800 controller, version 17.1.1t or higher. 9100 series access points, and 11AX capable clients. You may be wondering why these versions. And for the answer, I'd like to direct your attention to the right side of the screen. There are 4 elements: 1024 QAM, OFDMA, BSS color, and target wait time. These 4 features are part of the 11AX implementation that was completed on these versions. For the next screenshots, I worked on 8.10.130.0 and 17.3.1. Step 1. Set channel width to 160 MHz to increase bandwidth. Bandwidth and throughput are different concepts. Bandwidth is how wide the lane is, and throughput how fast traffic actually passes through that lane. Channel width or channel bonding takes a 20 MHz channel and multiplies it by 2, 4, or 8 in order to widen the lane from the APs to wireless clients. Channel availability and overlapping needs to be considered when selecting 160 MHz because if the spectrum allows for 24-25 channels, by bonding 8 channels per set, there are only 3 sets to distribute among APs to avoid co-channel interference. If coverage is fine and not all clients require higher speeds, this should suffice. But this scenario may be more troublesome in a high-density deployment where an AP can hear a dozen neighbors in close proximity, unless we have a method to deal with that. Step 2. By default, all MCS rates are enabled. 11AX introduced 2 new rates, MCS 10 and MCS 11. Remember how I mentioned throughput is how fast traffic flows? This is why MCS rates are here, because the higher the modulation coding scheme, the more speed you get on the same channel width. You can see the same MCS over and over with the small difference of the special streams. What this means is that the AP will be allowed to use all MCS rates at multiple special streams for a single or multiple clients. Ensure all are checked. Step 3. Although not directly required for high speeds, BSS color and target wait time are very helpful allies when dealing with wireless client management. Keep them enabled. While BSS color can help you decrease the transmitted power at which the frames are sent and reduce noise, TWT can help avoid unnecessary keep alives and just have a client negotiate not to be disturbed for up to 5 years. Step 4. If you go under the advanced settings of a WLAN, you will find a downlink and uplink option for both multi-user MIMO and OFDMA. Unlike the previous 3 steps, these settings are what the clients are allowed to use and they're not from the AP perspective. Multi-user MIMO is not recommended for high-density deployments. This is because if there are multiple high-end 11AX clients in the WLAN, they could take all the spatial streams from an AP, causing oversubscription and degraded performance for the rest of the left-out clients. By unchecking multi-user MIMO, the AP can more evenly distribute bandwidth and direct traffic to all clients without preference. For OFDMA, however, this is not an issue. The AP can work with both old-fashioned OFDM and the new resource unit-based OFDMA simultaneously. Therefore, keeping it enabled is a best practice. Verification and troubleshooting. I've divided this section into 3 parts. The first one is from the air. Here we have an over-the-air wireless capture. There are multiple ways of taking an OTA, and for this example, I've taken it using a MacBook's built-in wireless sniffer. If you take a look at the top, the blue frame, which is right below the green filter, shows several elements. Their source MAC address, which is the wireless 11AX client. The destination MAC address, which is the Cisco access point. The type of request, which is an association request to the SSID called AeroS-11AX. If we go further and take a look at the properties of that frame, under the HE or high efficiency capabilities, which are the 802.11ax capabilities, we will find the HE MCS and SSS or network elements set. There, the arrows point to what the 11ax client can do. In this case, up to 2 special streams with HE MCS rates 0 through 11. This means that the wireless client can do for both reception and transmission 11AX with up to 2 special streams. On the very bottom, we can see a vendor-specific tag, which tells us that it's a Samsung client. And it is, because I used a Samsung S10 phone. Verification and troubleshooting. Part 2. From the AP. Whenever a client associates, the AP is smart enough to know what type of client it is in terms of supported speeds. The command show.11 clients lists the associated devices and their max rate, which is the speed rate they can achieve at that moment in time. But this doesn't necessarily tell us what type of client it is. For that, if you run show client summary, it will show two additional columns that state the protocol used at the time of association and the highest protocol they are capable of using. Here, VHT or very high throughput means the client is 11AC, and HE or high efficiency means the client is 11AX. In order to see the complete details about the client connection, the command show controllers.11 radio 1 client and the MAC address displays a complete list of features and settings the client is capable of and currently using. For example, this client is capable of using VHT rates with up to 2 special streams, as we can see on the left side. Also, it's connecting at 80 MHz with a short guard interval. Now let's take a look at our 11AX client. Just like the OTA capture showed in the attributes, here we can easily see the client can use HE rates with up to 2 special streams. It is also connecting at 80 MHz with a short guard interval. But what does all of this mean? Let's take the official MCS table. Starting with the 11AC client running on VHT MCS9 2SS. The triangulation of the conditions of having the VHT under MCS9 and then the special stream column under 2 matching the MCS9 and also the column of 80 MHz with a short guard interval of 0.4 microseconds along with the MCS9 and 2 special streams gives the result of 866.7 megabits of connection speed. On the other hand, for the 11AX client, taking the same steps, the result is 1.2 gigabits of connection speed. And if the client was able to use all of these 8 spatial streams 11AX offers for a single station, the client could use up to 4.8 gigabits. Luckily, you don't have to go through this equation to figure out what speed you're getting because on the bottom of the output of the same command, the AP tells you exactly what speed your clients are getting. And guess what? It's exactly the same speed we just saw. 866.7 and 1.2 gigabits of speed. I want to take this opportunity to point out that for these speeds to become a reality, clients need a good RSSI and a decent SNR. The RSSI in the 30s means that the client is right next to the AP. So anything in the 40s to the 60s and an SNR higher than 25 would be good. But even so, no one can dictate that a rate is based purely on RSSI. Some of the challenges of high throughput is guaranteeing that you have a certain speed rate while the client is moving. Even if you run an OTA capture, you need to resolve the equation for all frames to know what speed the client had at a certain time and the RSSI. How are you supposed to know the rate the client is at if it's not static? Well, I'm here to tell you that now you can. Welcome the debug.11 client rate MAC address command, a real-time speed debug that shows you the client's rate by the second. Of course, with the final rate and not just the homework for you to resolve the equation. Let's take a look at this output. There are several columns for the received packets, the transmitted packets, the transmitted rate, the received rate, RSSI, SNR, and retries. I'd like you to focus on only 3 of them for now: the TX rate, the RX rate, and the RSSI. Notice how the RSSI is getting weaker because the client is moving away from the AP, but the data rate is actually better now, going from 526 to 650 megabits. This is because the AP is able to use a shortcut interval due to pristine RF conditions. If there were a lot of clients or collisions or multipath, the AP would fall back to a longer interval and the rate would decrease. In part, the risk of the shortcut interval sending so much data with a short period of pause may reflect on the SNR. Let's see another example of this debug. I want to clarify that these values are from the client perspective, not how the AP detects the client. Here, we can see a steady transmission rate of 520 megabits, but the reception rate went up from 526 to 650 megabits per second. Now a third snippet. Here it's even worse. The client is transmitting at only 292 megabits, but receiving at 866 megabits. Why? To answer this question, let me take all of this out of the way and show you an image. APs will frequently be stronger than the client and will hear clients better than clients can hear APs. And while you're thinking of this, I want to show you the third part of the verification and troubleshooting. From the client. If you have a speed analyzer application, I'd like you to ask yourself, what rate does it refer to when it shows 866 megabits? Definitely not the transmission rate. For 11AX clients, the numbers could be even more deceiving because the client can receive up to 1.2 gigabits of speed, but we now know that a file transfer may be slower than that depending on the client's point in space and time. And the last section is here. Takeaways. Although the focus of this presentation has been speeds, I believe it's worth noting the additional benefits of Wi-Fi 6. It's not all about speed, but if speed is needed, speed is great. We now know how the AP manages bandwidth and throughput for a single or multiple clients. As new clients come out, they'll be able to use 4 or even 8 spatial streams. And because APs can dynamically allocate clients with different spatial streams, for example, one client on 4 spatial streams plus 2 clients on 2 spatial streams, consider tweaking your settings or rethink your design. Next, power savings. Target wait time solves a long-standing issue with client battery. Instead of relying on DTIM, which would save power by skipping a few cycles of keep alives, DWT is a real negotiation or proposal of a fixed period of time in which the AP and client will not exchange any messages and the client can go to sleep, dramatically saving power. Low latency. OFDMA brings a new method of wireless transmission, and this transmission is now scheduled. When using OFDMA, the time wasted when collisions occur because everyone needed to wait before sending any traffic is practically gone. Moving towards a deterministic model. The lack of reliability in terms of timing or mechanisms to deal with unexpected disruptions from previous generations is addressed here for customers with voice or Internet of Things services where timing is of essence. And finally, higher client density. We know how to deal with clients in high density deployments in terms of speeds, but there is so much I want to say about this, and I will. Let us imagine a wireless deployment where these numbers do not represent a channel number, but a set of channels used by an access point. When using 20 MHz channels without any bonding, the risk of overlapping and co-channel interference is very low. However, as we strive to get higher throughput and widen our lanes, fewer sets are available to be distributed on neighbor APs, and the APs and clients start hearing other APs using the same sets of channels which are servicing their own clients. This phenomenon is called spatial reuse and can cause co-channel interference, and co-channel interference causes backoffs. Backoffs are an enemy of high efficiency because they not only stall the traffic of their cell, but they stall all traffic from anyone who could hear the frames on the same channel or set of channels. 11ax introduced a feature that has addressed this problem by assigning each IP and the clients of each IP a color so that when traffic is heard on the same channel, APs and clients check that value, and if it does not match, they discard it because they know it's not meant for them, and will keep transmitting, while a mechanism called OBSS packet detection works to regulate the power levels of the APs so that everybody can be in a safe transmission distance without causing backoff. This is called BSS coloring. With BSS coloring, it's possible to have a high amount of clients connecting at the same channels as some of their neighbors, and each one of those groups of APs with their own color can have simultaneous transmissions without fear of backoff. The fact that clients are always in sync with their AP and know their color naturally causes clients to reduce their power, bringing down the noise. And these are the consequences of having such an efficient environment. While Wi-Fi 6 shows a steady low latency voice network even though there is a very high client count, with Wi-Fi 5, as the client count goes up, the latency increases dramatically due to collisions. In terms of speeds, Wi-Fi 5 shows degraded performance as more clients are added to the AP, whereas on Wi-Fi 6, as long as it's not oversubscribed, the throughput is consistent. What's next? How can I address the signal reception difference between AP and client so that RSSI and speed is nearly or exactly the same both ways? Know your clients. A site survey is the first and most important thing in this case. An active site survey using the weakest client type to be used in the network ensures that coverage will not be an issue during production. Also, the placement of the APs depending on their antenna type is a big factor because radiation patterns change. The heights at which APs should be placed change. Finally, TPC levels can be tweaked possibly per RF profile so you have control of specific areas. I know my client specifications and throughput requirements, but an end-to-end solution will take time. Is 11ax an overkill for my network? Never. Even if there were 2960 switches, APs can dynamically scale down the spatial streams they can use to operate in medium or even low power modes. The AP's mGig port can connect at 5, 2.5, or 1 gigabit per second, and they also offer the possibility to work with BLE or IoT. And the last question of the final slide. I see the same speeds as 11AC. Why should I get all this new equipment? I love this question, and you're gonna love the answer. There are two max rates you can get depending on the modulation used when on 11ax. With 11AC on OFDM, you can get a maximum rate of 6.9 gigabits. With 11ax on OFDM, you can get a maximum rate of 9.6 gigabits. But with 11ax on OFDMA, you can get a maximum rate of 4.8 gigabits. If you use OFDM, you will get more throughput. If you use OFDMA, you get less throughput and apparently go slower. But if 11AC uses collision avoidance and has to constantly stop transmitting due to wait times, besides having wasted bandwidth assigned to clients who may never use all of it, then it doesn't look like a good deal. 11AX OFDMA assigns clients with the resource units they really need, so that they can transmit on a scheduled basis, eliminating wait times while naturally prioritizing critical traffic and saving battery power. With 11AC, you get bandwidth. With 11AX, you get efficiency.
This concludes the presentation. I want to thank you all for watching and see you next time.